Okay, hello again. Don't know whether it's a good morning, good afternoon, or good evening to you. We're going to continue our video sessions on computational strategies for the arithmetic of whole numbers. We just completed a couple of video sessions on the computational strategies for addition. We're now going to turn to the arithmetic principle called multiplication, reminding you once again that what we're trying to do is arithmetic principles like addition, multiplication, subtraction, division, or combinations thereof lead to a single set whose size we want to determine, and that single set's called the target set. So right now we're turning our attention to the multiplication principle, and we want to consider computational strategies that help us take an arithmetic expression and modify it in ways so that we can find the size of the target set without actually finding the size of the target set. So let's move to a little bit of explanation on the multiplication principle. You'll recall that the multiplication principle is really the addition principle, where the only extra requirement is that instead of just having arbitrary sized groups that we're going to merge together, the multiplication principle is one in which we have a group of objects or a set of groups of objects, but the requirement is that all these groups of objects have to have the same size. If you're looking at this slide where we're introducing the multiplication principle, I'm going to remind you that we have three groups of objects, but unlike addition, in multiplication, it's required that these three groups of objects have to have the same sizes. So on this slide, you'll see three groups of objects, and this time in each group, we have 8 beach balls or 8 colored balls, and once again, the multiplication principle says if I take all of these groups that all have the same sizes now and we merge them together into a single set called the target set, what is its size? Early strategies for kindergarten and first graders is once they form the target set, they will physically go through and start sequentially counting, or possibly skip counting by 2s, by 3s, or whatever. But they'll end up with a count, and in this case, 3 groups of 8 turns out to be a size 24. There's 24 beach balls or colored balls down in the target set. So this is what we want to turn our attention to, are computational strategies to finding sizes of target sets that emerge from the arithmetic principle called multiplication. As I've already said, sequential counting of the objects in the target set is one of the first strategies that kids learn. Or they might skip count. They might look at the objects in the target set, and they might pull them out 2 at a time and go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, which would be exactly what would happen if they were given the 3 groups of objects with 8 in them. Or they might skip count by 3, 6, 9, 12, 15, 18, 21, 24. They might even skip count by 5s, go 5, 10, 15, 20. Then those got 4 more, and so it's 24. So we've talked about sequential counting. We've talked about skip counting. And then we've talked about combination pairs for addition. And just as there are combination pairs for addition, there are combination pairs for multiplication. Before we talk about combination pairs, let's remind ourselves once again of the abbreviated notation that we use for multiplication. Remember, in the example we just looked at, we had 3 groups of objects in which there are 8 objects in each of the 3 groups, which is a requirement for multiplication. All my groups that I'm going to put together all have to have the same size. So here I have 3 groups of objects, and in each group there are 8 objects, and all the objects in all 3 groups have a common unit of measure. Could be cookies, could be ping pong balls, could be Pokemon cards, it could be houses, whatever. So if I merge those together, what's the size of the target set? Well, we're going to streamline this notation, and what I'm going to do is indicate first with a number how many groups I have. In this case, there are 3. And the second number is going to be the size of each of the groups. Since it's common, I only need one number. And so this is going to be an abbreviation to the notation where I have 3 groups of objects, and each of the groups has 8 objects in it. So the first number will represent the number of groups, and the second number will represent the size of each group. And of course, what we want to know is if we take these three groups of objects and merge them together into a single group called the target set, how big is it? And so combination pairs are pairs in which lead to a friendly number. And so it might be such things as 2 times 5, because we know that if we have 2 groups of size 5, and this of course is equivalent to 5 plus 5, we know that's going to be 10. That's a friendly number. It could be 5 times 2. And 5 times 2 means I have 5 groups each of size 2. So this really means that I have 5 groups each of size 2. But that's 5 times 2 is our abbreviated notation. And when I want to know how big that is, well, that's 10. So again, any pair of numbers where the multiplier is the number of groups and it's the number given first, and the multiplicand, which is the second number, it's the size of each group. If that product ends up being a friendly number, then we call that a combination pair. So 3 times 5, which means 3 groups each of size 5, we want to know how big that is. And the kids might even skip count on this. They might go 5 plus 5 is 10 and 5 more is 15. So they know this is 15. So anytime a combination, anytime a pair of numbers that we multiply together. So here is the first number, and I'm going to call it S. And second number, I'll call it T. If that product ends up being a friendly number, F, friendly number, maybe I should write it out, friendly number, then that's called a combination pair because its product produces a friendly number, just like an addition. If we add 2 numbers together and it gives you a friendly number, that's called a combination pair for friendly numbers. So these kinds of number pairs for multiplication, these are the ones we want our kids to learn, not memorize, but learn through experience. So again, let me go back to our document to make sure that I'm staying focused and staying online. So we've talked about combination pairs. Let me just say this about subitizing. Subitizing is any pair of numbers that we multiply together whose product we know the answer to. Well, this builds us a list that by the time they're at the end of 3rd grade, they're supposed to know all their single-digit and double-digit multiplication facts up through 12. So those are to be learned, and those become what's called not combination pairs, but compatible pairs or multiplication facts. And these are the ones we want them to learn, not memorize. I know there's a lot of teachers and a lot of individuals who feel like kids should memorize these. I'm not a believer in memorizing because memorization is something that's very difficult to recall later. So if things are learned so that they make sense to the kids, that's a better way to do it. We're going to talk about backup plans for multiplication facts in a little bit. But right now I'm going to go back and remind you and remind us about the any order property. So we want to talk about the any order property. And of course we're in the arithmetic principle called multiplication. So the any order property says if I have some numbers that I want to multiply together, like 5 times 7 times 2, and I want to know what that product is, I have to understand that in this symbolism, I've got to do something first. And so in the absence of any parentheses, it might be that I want to find out if I have 5 groups and their size is represented by 7 times 2, how big is the target set? Or it could be, I could look at it a little bit differently and put the parentheses around the 5 and the 7 and simply say, if I have 5 groups each of size 7, and that represents the number of groups that are of size 2, what's that product? Well, it turns out that no matter what order I pick, according to Piaget's conservation number, no matter what order I choose to form these products, I'm going to get the same size target set. Now, some of these products are better. For example, in the 5 times 7 times 2, I'm going to put the 5 and the 2 together first. Then I'm going to multiply it times 7. And why would I do that? Why would I choose to put the 5 and the 2 together? Well, the 5 and the 2 together is actually a combination pair, and 5 times 2, or 5 groups each of size 2, turns out to be 10. And then 10 times 7 is a friendly number times 7. It's actually a power 10 number times a single digit number, and kids learn in the second grade that that's 70. So the any order property allows us to put numbers together if we're forming a product among 2 or more numbers. I selected 3. It could be 4. It could be 5. I get to choose the order in which I form the multiplication. And that's the any order property, and it's a very valuable property, just like the any order property for addition is. I get to pick the numbers I want to put together in the order, and once again, you can draw a picture to illustrate this fact, that the any order property is true for multiplication. Let me go back to my list again to make sure I'm staying focused. So on the list, we've talked about sequential counting, skip counting, combination pairs, the any order property, subitizing, compatible pairs. Those are the pairs that we learn, and through experience and through learning, we come to know multiplication facts, but not through memorization. I don't think that's a good way for kids to learn their multiplication facts. So let's back up and look at some multiplication facts, or some what might become compatible pairs for our kids. So let's go back to our whiteboard. Now, through experience, the kids will learn that if they're trying to find 2 groups, each of size 3, or if they have 2 boxes and there's 3 cookies in each box, that if we put the 2 groups of cookies together, they'll end up getting a box of 6 cookies. Or it might be something that 3 times 5, they know that this means 3 groups, each of size 5, so they could go 5, 10, 15. So just by understanding what this means, that this means 5 plus 5 plus 5, they get a count of 15. By the way, let me emphasize something. That does not mean 5 times 3. That's not what that notation means. Remember, the first number represents the number of groups. The second number represents the size, and there's no exception to that rule. That's the definition of multiplication. Now, it turns out that 5 groups of size 3, which means something entirely different than 3 times 5, it is true that the target sets are the same size. So the target set for 3 groups of 5 has the same size as the target set for 5 groups of size 3. The product is 15. But remember, make sure you kids understand the difference, that 3 times 5 and 5 times 3 mean completely different things, but the size of the target sets are the same. Now, these are things that are easy for the kids to remember. And it might be that 4 times 6 might be an easy one to remember. This means 4 groups, each of size 6, or 6 plus 6 plus 6 plus 6, and they might remember that's 24. Now, what I want to do is, when they're looking at their multiplication facts, which in Tennessee, the multiplication facts must be learned by the end of grade 3. In your state, it might be different. But the multiplication facts are to be learned by the end of grade 3, and we want our kids to learn them, not memorize them. But we also want them to understand that if they can't remember, for example, what 8 times 6 is, or they can't remember what 9 times 7 is, we don't want them to freeze up and freak out because they don't remember what that is. It's not a big issue. that they can't remember what that is. They're adults that can't remember what 8 times 6 is or 9 times 7. But here's what I want them to have. I want them to have a backup plan. I want them to be able to figure that out based on their understanding of multiplication and place value. So when we talk about these, I want to make sure they have what's called backup plans if they don't know what these are. And the backup plans depend on place value and what's called decomposition. Decomposition. Okay, so what does that mean? Okay, so let's talk about decomposition. If I did spell facilitate correctly, you can fix it for me. Decomposition to facilitate computations. Okay, let me see if I can illustrate what I mean by that. Let's suppose I have 3 groups of 6. So here I have 3 groups, and notice that size 6, and let's suppose they're cookies. So I have 3 groups of size 6 cookies. So here's a group, here's a group, here's a group, here's a group. So 3 groups of cookies. There's 6 cookies in each of the groups, or it's 3 boxes of cookies, and there's 6 cookies in each box. What would happen if I took those 3 groups of cookies and merged them together into a single target set? How big would it be? Well, I'm going to illustrate this idea of decomposition, which is based on place value and Piaget's conservation number. I'm going to rewrite them again because I've already put those ellipses around them. They're not ellipses, they're just squashed circles. Okay, so here's our array of cookies. I have 3 groups. The top row represents one group, the middle row represents a second group, the third row represents a third group. Okay, and what I'm going to do, and I'm going to experiment here and see if I can't pick a blue pen. And what I'm going to do is I'm going to take this group of objects, and remember Piaget's conservation number says no matter how I arrange or rearrange these objects, I will not change the size. Okay, so here's what I'm going to do. I'm going to separate these groups of objects into 4 groups of objects. So instead of having 3 groups of objects, I now have 2 groups up here and 1 group down here. Instead of having size 6, I made it so these are of size 5 up here. This is size 1. And here's what I claim. I claim for some students, figuring out how many objects are in this first group, and how many objects are in the second group, and how many objects are in this third group, and how many objects are in this fourth group, is easier than finding how many objects are in these 3 groups over here. And the reason is, in this one, there's 2 groups of size 5, so we know that that first group leads to 10. In this one, it's 2 groups of cookies. In this one, it's 1 group of 5 cookies. And the last one, there's 1 cookie sitting there. And my claim is that adding these groups in the smaller sizes, 10 and 5 is 15, and 2 is 17, and 1 more is 18. So I know that 3 groups of size 3 groups of size 6 is the same as 18 cookies. And I did it by partitioning my array into subarrays or subgroups that I can do the calculations easy. Now, this is precisely what's called the table array strategy for multiplying bigger numbers together, but I thought we'd look at it in a smaller way, because this is the idea we want to use in learning our multiplication facts if we don't know. For example, if you don't remember what 8 times 6 is, I want them to be very clever about how to figure out what 8 times 6 is. Or if they don't know what 9 times 7 is, I want them to use a backup plan using place value, decomposition, and I should add here Piaget's conservation of number, which allows me to move the objects around so I can facilitate the computation. I want to use it on 8 times 6 and 9 times 7. So let's see how we can do that. Let's suppose they can't remember, for example, that 8 times 6 is whatever it is, okay? So let's get us a new screen. So we're looking at 8 times 6. Now I want to know how big that is. Well, remember, this means 8 groups, and the size of each group is 6. Now, I want to find 8 times 6. So if I were to do this, I'm going to do it with pictures, but after I do it this next time, that should be enough to generalize to bigger numbers, okay? So the idea is I've got 8 groups, and there's 6 in each. And I think it's important to go through this picture, so bear with me. Let me take the time to put this array of 8 groups of 6 dots, or we can think of it as 8 boxes, and I've got 6 cookies in each box, or it could be 8 boxes and I've got 6 donuts in each box. So right now I've got what? 1, 2, 3, 4, 5, 6. There's my 7th box. And here's my 8th box. So there's the number of cookies that I get when I take all 8 boxes of cookies, 6 cookies in each box. If I merge them together, here's what I get. Now I could count these sequentially. Kindergartner and first graders would do that, okay? But I want to figure out a slick way for doing that. Here's what I'm going to do. I'm going to pick me another pen color, and let's suppose I make it red or orange, whatever it turns out to be. And I'm going to take the 8, and you'll see why I'm going to split it up the way that I'm going to split it up in just a moment. I've got 8 groups, but what I'm going to do is I'm going to split it up into a group of 5 and a group of 3. And instead of having size 6, okay, so I partitioned it right here. And what I'm going to do is I'm going to split it up. I could stop right there and say, okay, what I have right now is 5 groups of size 6, and they may know that this leads to 30. They may remember that 5 groups of size 6 is 30, and they may remember that 3 groups of size 6 is 18 because they just got finished working the problem from before. So they may see that 30 plus 18 is, 30 and 10 is 40, so it's 48. But let's suppose they don't see that 5 times 6 is 30, but let's suppose they want to partition it this way. And by the way, I'm making a choice. The kids get to make this choice. I'm partitioning there. So now I have 4 groups. The first one is 5 groups of 5, so that's 25. The second one is 5 times 1. The third one is 3 times 5. That's 15. And the last one is 3 times 1, which is 3. And then all I have to do is add those together. Okay, and then now that what remains is just to add the number of cookies in each of the 4 groups, which is 25, and 5 is 30, and 10 is 40, and 5 is 45, and 3 is 48. Now, I did that sort of using mental math. If they want to formally add these together, fine. But however they put those three groups together, they're easier to put together than remembering that 8 times 6 is 48. Is this the only way we can decompose both the multiplier and the multiplicand into two parts to facilitate the arithmetic? No, there are, probably 20 different ways. So what I did is I took the 8 times 6, and I want to figure out what that product is. So I split the 8 up into 5 plus 3 times, and then I split the 6 up into 5 plus 1. And the reason I chose these is that 8's not a friendly number, but 5 is a friendly number. So I decomposed 8 into a friendly number plus 3. I decomposed 6, which is not a friendly number, into a friendly number plus 1. And the reason for doing that is now when I form the multiplication, this will become 5 times 1 plus, 5 times 5 plus 5 times 1 plus 3 times 5 plus 3 times 1. And so again, I've written down what we're actually doing in an abstract way. So this leads to 25 plus 5 plus 15 plus 3. And that turns out when I do the arithmetic to be 48. So these are called backup plans. If I don't know what 8 times 6 is, I've got a way to figure out what it is. The other one, I think, if I go to a new page, I think was 9 times 7. And if we don't remember that 9 times 7 is whatever it is, 63, I think, okay? 9 times 7 is 63. They can figure out what that product is if they're required to find 9 times 7 just on the basis of understanding that it means 9 groups, each of size 7. They could take and add 7 to itself, 7 plus 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 7, and figure out what the sum is. But I think there's a better way. I'm going to take the 9, okay, and I'm going to write it as 5 plus 4, and I'm going to take the 7 and I'm going to write it as 5 plus 2 equals, and so I'm going to work this problem rather than this problem up here because I think it's easier. And this is not the only way to do this problem, but let's see. This is 5 times 5 plus 5 times 2 plus 4 times 5, and finally 4 times 2. And we want to know what that is. Well, let's see. 5 times 5 is 25. 5 times 2 is 10. 4 times 5 is 20. And finally 4 times 2 is 8. I want to know what that is. Well, let's see. There's 25. 20 and 20 is 30. So I have 25 and 30. So that is 50, let's see. 25 and 30 is 55. And I'll take 5 from 8 and make it 60. And 3 more make it 63. So this ends up being 63. These turned out to make it 55 plus 8. And that was 63. Is that the only way? No, it could be that if kids like to work with 10s, instead of finding 9 7s, what would happen if they found 10 7s? 10 7s is 70, but you only want 9 7s, not 10 7s. So this number is 7 too big. I found 10 7s, and I want 9 7s, so this is 7 too big. So 9 7s must be 7 from that, or 70 take away 7, so that's 63. There's 2 different ways to find 9 times 7. Those are called backup plans, and they're all based on Piaget's conservation number, decomposition, and you can choose to either decompose the multiplier, decompose the multiplicand, or both. So let's see what's left in our computational strategies for multiplication, especially as we begin to look at larger numbers. In fact, while we're here, I think we've talked about decomposition or break apart. We talked about backup plans. Mental math, again, is doing the arithmetic in our heads. And if we're capable of doing that, we'll really focus on place value to do that. So I'm going to skip over mental math, and I'm going to turn to value expanded form, place value expanded form, except I'm going to do just value expanded form, and you can do place value expanded form. So I'm going to look at value expanded form. Let me give a new sheet. So I'm looking at value expanded form. And so let's suppose that I'm going to jump up now to some reasonable size numbers. Let's make 23 times 47. I'm going to guess that's not a compatible pair for anyone in the audience. They don't know what 23 times 47 is automatically. In other words, if they have 23 crates, and each crate are 47 oranges, let's say, so if 23 crates, there's 47 oranges in each crate. If I merge those 23 crates together, then what's the total number of oranges that I have? Well, I want to figure this out, except I can't handle 23 times 47 all at once. So what is it that I'm going to do? Well, I'm going to split it up. I'm going to put my multiplicand on top, and I'm going to write it as 40 plus 7. And I'm going to put my multiplier on the bottom, although it doesn't have to be because of Piaget's conservation of number. So I'm going to write it as 20 plus 3. And now I've split the 23 into 20 plus 3 and the 47 into 40 plus 7. And I like this decomposition because these numbers now fall into the category of what? Either friendly numbers, power 10 numbers, or single-digit numbers. And so I'm always working with either one of those three, two of those three, or all three of those three. So once again, as we've asked our kids in kindergarten and first grade, or coach them, I'm going to start with the larger numbers. So the first thing I'm going to do is I'm going to find 20 times 40. Well, 20 times 40 is 800. And then I'm going to find 20 times 7. And 20 times 7 is, well, let's see, let's back up. On this problem right here, you might be asking, well, how do I know that's 800? Well, remember the any order property, and the 20 times 40, this means 2 times 10 times 4 times 10. And the any order property says I get to multiply those in any order that I want. I'm going to choose the two single-digit numbers 2 and 4, and so 2 times 4 is 8, and then 10 times 10 is 100. So this is really 8 times 100, because I got to put the numbers together in any way that I wanted to. So I'm going to choose to take 2 times 4 is 8, and then the 10 times 10, and get 100. And so that's the reason I got 800, or that's how 800 came about. Same way with 20 times 7. If I don't know that that's 140, I could split that up into 2 times 10 times 7. And so in this multiplication, I'm going to do the 2 times 7, which is 14, times 10, well, it's 140. And then I'm going to move to the 3, and so the next one will be 3 times 40. And once again, I could write the 4 as 4 times 10, and it becomes 12 times 10, or 120. And 3 times 7 is 21. Then I'll add together, okay? And remember the way we added for addition, we added left to right. So this would be 8 100s, 9 100s, that's 1,000. And then I have 40, and that's 80. And then I have 1. And so 1,081, so 1,081 is the product of 23 times 47. And again, it's because I don't know this product. I don't know, this is not a compatible pair for me, but the idea is to use decomposition, and I used value expanded form by taking the 23 and writing it as 40 plus 7, and 47 as, the 40 as 40 plus 7, and the 23 as 20 plus 3, and went through the multiplications. Instead of doing two numbers together, I split it up into 4 groups and did 20 times 40, 20 times 7, 3 times 40, and 3 times 7. And those 4 groups, those 4 products are easier to compute than trying to do 23 times 47 all at one time. That's value expanded form. And value expanded form leads to table array, just like value expanded form for addition led to table array form for addition, multiplication and value expanded form leads to table array for multiplication. So let's turn or illustrate 23 times 47 and then maybe a bigger product. And so we'll do it not with value expanded form, but for table array. So let's do this in table array, 23 times 47. So 23 times 47. And what I'm not doing is I'm not formally writing out the value expanded form for 47 as 40 plus 7, and I'm not formally writing out the value expanded form for 23 as 20 plus 3. I'm just going to do the arithmetic on the fly. As before, we're working with the larger numbers. We're doing arithmetic from left to right. So the first thing is 20 times 40. You want to write it out here to the side and ask your kids to do this to show you, okay, what they're doing. I could write 20 times 40. And then it's 20 times 7. And if they don't know that's 140, let them take the time to go ahead and expand that to show why that's actually 140. So the 20 is 2 times 10 times 7. So they could do the 2 times 7 because of the any order property. 2 times 7 is 14, and 14 tens is 14 tens or 140. Then finally, 3 times 40, which is 120, and 3 times 7, which is 21, which is 21. And as before, when they went through and did the arithmetic, this turned out to be 1081, I think. Yeah. Okay, now this is table. This is table array. Let's do one more, except let's change the size of the numbers. So if I were to do, let's take 38 times 427, and I want to find, if I have 38 crates and each crate are 427 ping pong balls, if I were to take the 38 crates or 38 boxes, each one having 427 ping pong balls, and put all those 38 crates together, what's the total number of ping pong balls that I have? In other words, what's the product of these two numbers? Again, we would write this as 38 times 427. So the 3 is not 3, but 30. And I'm multiplying not times 4, but 400. So what's 30 times 400? Your kids, through experience, not because you're telling them a rule, but through experience, they're going to figure out, well, this is just going to be a 12. And I've learned from experience that if I've got a number with 1 0 and a number with 2 zeros, my product's going to have 3 zeros in them. Don't tell them that. Let them discover that on their own. Let them figure out that that's the case. So this is really a 12 followed by 3 zeros. So this is 12,000. Then they're going to do 30 times 20, which we get 600. Then they're going to do 30 times 7, which is 7 3s, 21, and 1 0s, 210. Then they're you're going to drop down to the 8. Then they've got 8 times 400, which is how much? Well, it's 8 times 4, which is 32, followed by 2 zeros, so it's 3,200. And then 8 times 20. That's what, 16 and 1 0, which is 160. And finally, 8 times 7, If they don't know that it's 56, then they go up here and they're going to figure out what 8 times 7 is. They're going to use some backup plan to figure out what 8 times 7 is. It could be one where they say, well, let me find 4 times 7. I know what that is. 4 sevens is 28, and I want 8 sevens, so I've got 4 more sevens to find. That's 28. And these two together are 40 and 16, which is 56. So they're going to figure it out as long as they know what multiplication means and they understand Piaget's conservation of number and break apart a decomposition. And then they go through and they will add using table array form, okay, to add these numbers together from left to right. Now, I'll let you finish that. But this is called table array. Look back at our chart, see where we are. We talked about backup plans. We talked about mental math. We talked about value expanded form, which led to table array form. We skipped over place value expanded form, but it's just doing your calculations using place value rather than using value expanded form. And all of these, of course, are built around a full understanding of place value. One more to go, and that's the lattice array. So let's go do lattice array. Let's get us a full screen. And let's do the same product. 38 times 427. And let's use lattice array on this one. Okay, so it's 38 times 427. So let's get us a new page. It's called a lattice array. Let me pause and talk to you for a moment. Why are we looking at different computational strategies? Well, again, what is one of the most important ideas that you should embrace as a teacher is that kids are different. In your classroom, there are no two kids the same. They don't think the same way. They have different experiences. They're coming from, if you're teaching this in 4th grade, they've come through, 2 of those kids have come through different kindergarten teachers, 1st grade teachers, 2nd grade teachers, 3rd grade teachers. And so their experiences are completely different. And the way that they think has been modified and molded by different teachers. And what you want to be able to do is, if a kid's not getting one particular computational strategy, give them another perspective. Give them another way to look at it. Give them a strategy they might like because it involves drawings or graphs that look to be non-routine. They look to be cute to them. You know, you're going to have those butterflies in your classroom. You're going to have those artists in your classroom, and they like to draw things. So we're looking at multiple perspectives so that you have a way to address the needs of different students. It's called differentiated instruction. You want to have different ways of thinking about things, doing computational arithmetic, different strategies that they can find sizes of target sets. And by the way, it's not just that you've got these methods. Your kids may come up with methods. It has in my time in working with elementary teachers for the last 15 years, they've brought to me new strategies I've never seen before. In fact, I'm going to share a couple of those in the next few videos that we're going to put together. And so you'll see strategies that my kids have learned or developed on their own and brought to my classroom, and I like them, and I share them. Because they're the best? No, but because they're different. And there may be a kid who looks at that and says, wow, that makes perfectly good sense to me. That's the one I'm going to use. Because what we want them to do is to embrace ideas about mathematics, computational strategies. We want to embrace things in such a way that makes sense to them, because the things that make sense to them, those are the things that are going to stick. It's not the things they memorized. The things they memorized are gone by the end of recess. Okay, but the things that they understand, that they see, they like, that'll stay with them forever. So let me give you one more strategy called the lattice array. Let me go back and see what the numbers again are: 38 and 427. And actually, this is going to end up being just another way to look at the table array, but it's sort of like in diagram or picture form. So here's the multiplicand I wrote at the top. Does it have to be written at the top? No, it doesn't. It could be written along the side here. So over here I put the multiplier, 38, and up here I put the multiplicand, 427. But I could put the 38 up there and put the 427 along the side. Doesn't make any difference how I do it, but I've chosen to put the multiplier on the right-hand side. And then with these boxes that are supposed to be squares better than rectangles, I'm going to do this. And here's what we're going to do. This is pretty much like the lattice array for addition. Remember, we can do the multiplication in any order that we want to. I want to focus on the left to right order, but you know, if they want to start in the middle or move from right to left, it's okay. So I'm going to start in this upper left-hand corner. Remember, that 3 is not a 3 but 30. That 4 is not a 4 but 400. But I'm going to just say 3 times 4 is 12. Now the question is that 12, is the 1 and the 2 in the right position? Well, remember, in this diagonal, this was the 1s, this was the 10s, this is the 100s, this is the 1000s. And this is the 10,000s. So here's the 1s, 10s, 100s, 1000s, 10,000s. And if you remember, 30 times 40 was actually what? 12,000. So that 2 is in the right place. It's in the thousands column. And that 1 is in the right place. It's in the 10,000s column. So actually, this is a slick diagram or strategy to help the kids keep track of place value. So again, doesn't make any difference where I go to next. It could be 3 times 2 is 6. That must be a 0. 3 times 7 is 21. Now, I'm really not saying what it is, because really it's 30 times 7, which is 210. So that's probably in the hundreds column. It is. And this is in the tens column. It is, or the tens diagonal. So I'm calling these columns when they're actually diagonal or diagonal columns. Okay. So 8 times 7, 56. 8 times 2, 16. 8 times 4, 32. So what I'm doing is I'm putting those products in their boxes, and I'm actually ignoring their value. I'm ignoring that when I multiplied 30 times 40, I wanted to make sure that that was 12,000, so I want to make sure the 1 was in the 10,000s diagonal, and I want to make sure the 2 was in the thousands diagonal, and so on. This kind of array does it automatically. It helps the kids put these products, these 6 products. Remember, here's a 2-digit number, here's a 3-digit number, and those products will lead to 6 groups, and here they are, one of size 56, one of size 210, one of size, and so on, 160, and so on. Now, again, I'm going to let the diagonal columns take care of their arithmetic. So this is 6. Now remember, this is the tens column. So it's 6 tens and 5 tens is 11 tens, and 1 10 is 12 tens. This is the hundreds column. So this is 6 100s and 2 100s, 8, 9, and 2 more is 11 100s. And this is in the thousands column. So it's 5 thousands, and finally the 1 is in the 10,000s column. So all I have to do is, and since I'm kind of a person finicky on perfection, I didn't want that mark to stay there. So now I have to do is just accumulate so I can put the product in standard form. So here, this was 12 100s, so I'm going to leave 2 here and push 1 over to this one. So this is 12. So it's 12 100. So this is in the tens column. So this was a 100. I put it over here. So I got 12. So I'm going to leave 2 here and put the 100 over here. It's actually 1,000. Put it over here. So that's 1 more. So that makes it 6 and 1. So if I think I've got things straightened out, I should have 1/10,000, 6,000, 226. And that's assuming I didn't make any careless mistakes when I went through that. So in these products, I got 6, 12, 11, 5, 1. So this should be, leave the 2 here, move 1 over here. That's 12. Leave the 2 here, move 1 over here. That's 6. And there's 1. So it should be 16,226. And this is called lattice array. Is it a great strategy? A great computational strategy? No. But it is a strategy where it helps the kids keep track of place value, and they may like it simply because it involves a diagram or a picture where they're drawing lines and they're following a little game plan here. And some kids will love this. Some kids say, no, I don't like that. And that's okay. The kids are different, okay? But you want to make sure that as a teacher, you're prepared to offer different plans, different perspectives to give your kids ways to find the products, okay, when they're multiplying numbers together, especially larger numbers like 38 times 427. Okay, the next arithmetic principle we're going to look at is subtraction. And it's my all-time favorite among the addition, multiplication, subtraction, division. I love subtraction because kids struggle with that. And I think it's just because of the way it's presented. And I will present strategies that have nothing to do with borrowing. And so we sort of think of like, no more borrowing ever. And so that's what we're going to do when we move into the next principle called subtraction. Have a good day.